Okay, yeah, the stream is set up. So we are also live on YouTube, but we can stay on Zoom.
All right.
Yeah, the stream is set up. So
great. Yeah.
also live on YouTube.
Yeah. So maybe it's good. It's good to start. I'm very glad to introduce Gil Kalai, a professor from the mathematics department at the Hebrew University. And on a personal note, he was my teacher as well. And I've been following Gil's talks on quantum computing for quite some time. And there are also very good blog posts that you can find on his website. And since Ethereum had a previous talk by Aronson, who you could say is a quantum computing optimist, we thought that it would be good to have a talk by a critic. And
parce que là, en fait, beaucoup des...
And yeah, so without further ado, I'll just let Gil present his thesis. The structure of this call would be 60 minutes talk by Gil and then 30 minutes Q&A. So Gil, go ahead.
Okay, thank you very much. It's a pleasure to be here. And soon I will also share a presentation. I thought about the following structure. So I have a presentation, introductory presentation for about 30 to 40 minutes. And you can ask questions also during this time. And then the presentation is larger and it contains 5 different parts that probably will not be able to cover all of them, but according to your interest or question, we can zoom in on 1 or 2 of these parts. And I don't have a limitation except that I go with my grandchildren to a basketball game, so I have to leave at 7, but I think we will finish as scheduled after 90 minutes. And let me move on to my presentation. So share just a minute. So a critical view on quantum computing. So again, my name is Gil Kalai, and I am from the Einstein Institute of Mathematics at the Hebrew University of Jerusalem, and also at the Efi Arazi School of Computer Science in Reichman University. And the question, so let me try to organize the Zoom so they will not disturb me all the... Okay, so quantum computers, as you know, are fascinating, hypothetical, powerful computers, and the debate regarding their possibility represents one of the most important scientific problems of our time. My theory asserts that building quantum computers and even reaching significant milestones toward them are fundamentally impossible. See, 1 minute. Move it to some place. Okay, so in minutes. Yeah, I think my presentation is freezed, so let me try to unshare. and share again. Now, this happens from time to time. So I'll see. Okay, here's a one slide overview of my argument. So let me try to fix this. Noisy. So the crux of the matter is to understand noisy quantum systems or quantum computers in the intermediate scale. And my analysis is based on a two-scale, it's a two-scale analysis. And the noisy intermediate scale quantum systems, briefly called NISQ systems, represent a low-level computational ability that will not enable quantum error correcting codes that are needed for quantum computation. The novelty in this argument is that we use computational complexity reasoning to deduce limits for engineering efforts. We are used to the application of computation complexity to deduce limits for algorithmic or programming efforts. And this is sort of new, and the relevance of this approach will be tested in the next few years and the next few $1 billion that are invested to this endeavor. So here is a brief sketch that I may get to in more details about the computational power. You can see on the left the hierarchy of computational classes, the standard hierarchy of computational classes. So you can see P, which is the polynomial time algorithm. P belongs to BQP, which represents the power of quantum computers. And actually, BQP represents several classes for specific algorithmic tasks. You can see NP, which is much larger than P. It contains problems which are intractable, both for classical computers and for quantum computers. And NP is part, here we are out of scale, of the polynomial hierarchy, which is much, much larger computational class. And BQP even goes beyond for certain tasks, go beyond the entire polynomial hierarchy. Inside the polynomial algorithm, you can find what's called the bounded depth computation. This is bounded depth Boolean circuit, classic circuit. This is a classical, very limited classic computational class. And inside this class, Guy Kindler and I identified a subclass, which we call LDP, low degree polynomial. And the computational power of NISQ computers is subset of this low computational power. So I want to draw your attention. We had recently a debate under the name of Quantum Duel at Prague, where Matthias Christandel represent the optimistic or the realistic, in his view, opinion. And he pointed out that qubits are real. People are already able to build small and noisy quantum bits. And we need just better, let me read you his stance. For full-scale quantum computers, we need more and better qubits. This is difficult, but Matthias argues that there are no theoretical obstacle that we know of for this task. And my view is that building scalable quantum computers and even achieving early significant milestones toward quantum computation is fundamentally impossible. And this early significant milestone is quite important because this is something which is much, much below full-scale quantum computers, and it is things that people try to achieve in the fairly near future, and this will give us a test where this endeavor is going to. So let me present 4 predictions about quantum computers. Again, if you have questions, you can, let me try to, if you have questions, you can interrupt me. I'll try to, okay, so the first prediction asserts that qubits and gates will inherently be noisy. Engineering efforts to reduce this noise will encounter a barrier that prevents achieving the quality required for quantum fault tolerance. 2 qubit gates are especially important because to have universal computation, you need 2 qubit gates, and also in practice, we know that this is the most difficult component to control. And this means that the so-called quantum fault tolerance threshold that I may mention later, probably many of you heard about it, cannot be reached. So this is the first very concrete prediction that I make. The second prediction is a bit technical, but I would like to mention it still, is that cat states or maximally entangled states will inevitably experience substantially correlated errors. So this means that if we have entangled pairs of qubits, then the noise operator that correspond to them is substantially correlated noise. And this is a consequence of the impossibility of quantum fault tolerance. The third and the crucial ingredient or prediction is the following. Samples generated from quantum computers in the intermediate scale, and in particular from so-called boson sampling, correspond to a primitive computational complexity class called LDP, low degree polynomial, and as a result, they are incapable of demonstrating quantum supremacy or achieving high-quality quantum error correction. This argument, and as I said before, imposes a computational complexity-based limit on the engineering effort to reduce errors in NISQ computers. This prediction number 3, is what logically implied the first prediction, that we cannot reach low levels of noise for individual components. The fourth prediction, which complement the third prediction, assert that for small quantum circuits, we will experience noise sensitivity. So this reads as follows. The empirical distribution of samples obtained from 12-qubit random circuits inherently contain a significant noise-sensitive component. This means that the empirical distributions are necessarily non-stationary, changing over time, and are inherently unpredictable. And the noise sensitivity complement the prediction number 3 about the low-level computational power of robust distribution arising from NISQ computers, and it is also quite important, and the mathematics behind prediction 3 and prediction 4 is quite similar, and we may get to it later. Okay, so now I think the debate that took place 2 weeks ago with Matthias is a good anchor to explain the disagreement and also the agreement. And so let me mention the first disagreement between Matthias and I. Matthias claimed that for a full-scale quantum computer, we need more and better qubits and gates. And I think the crucial thing is not more, but better. And my view is that I agree that we need better qubits and gates, but I argue that it is inherently impossible to build qubits and gates of the required quality. let me move to the second points of partial agreement and partial disagreement. Matthias argues that there is no theoretical obstacle that we know of for achieving full-scale quantum computers. And my view is that I agree that there is no definite theoretical obstacles. However, there are serious theoretical concerns that need to be noted. And in addition, my theory gives a plausible theoretical framework for the impossibility of quantum computers. The debate will largely be decided experimentally, although it is also important to find theoretical consequences of both points of view. Let me mention briefly other skeptical claims. And here you can see a picture of several noted skeptics, and also two of my colleagues, which are largely optimistic. So on the top left, you see me with Michel Diakonov. Diakonov is a physicist, and he believes that quantum computers is an absurd idea from the physics point of view. On the right, on the top right, you find Robert Alinsky. He is also a physicist, and he actually wrote several papers over the years with concrete concerns from physics regarding the possibility of quantum computing. On the top, on the bottom, you see on the left Oded Goldreich, and on the right Leonid Levin. They had very negative opinion about the possibility of quantum computers, largely based on the computational complexity, fantastic possibilities of quantum computers, but also based on other arguments. And they simply claim that the abstract model of quantum computing is unrealistic. And in the middle, you can see me and Robert Alinsky together with Michael Ben-Or and Dorit Aharonov. Michael and Dorit are my colleagues at the Hebrew University, and they proved the threshold theorem, which is important in building quantum computers, and it also would be important in understanding the impossibility of quantum computers if this is the way things will turn out. So let me mention briefly some earlier skeptical claims. For example, the first claim that quantum computers violate the extended Turing thesis that represent our understanding of the computational world. So they will enable to factor integers in polynomial time, in n-squared time, and this is fantastic. And this led Levin, Goldreich, and others to doubt that this is a realistic model of computation. And the response is usually, yes, indeed, this is a feature, not a bug. We'll be able to do the computation power of our universe is much stronger than we thought of. There are other answers. For example, some people, and that I'll mention a bit later, and actually some people even thought that maybe, or still think that maybe there is an efficient classical algorithm for factoring. Something that was realized about later in 2000, sorry, I'm jumping. Another physics argument that raised by Alinsky is that quantum computer is in tension with the so-called time energy uncertainty principle. And the response to that is that the time energy uncertainty principle is a misconception, and Shor algorithm clearly shows it. So here we have a physics principle that many physicists adopt, some physicists doubt, and there is a debate about it. There was a debate about it even before quantum computers, and now the Shor algorithm somehow led some people to the conviction that this is simply a misconception and not a correct physical law. Another argument by Alinsky is that quantum computation is in tension with thermodynamical principles. And you see, intuitively, the ability to build arbitrary quantum evolution based on gates enable you to do things which looks rather fantastic from the thermodynamical point of view. In particular, everything that you can build, you can also reverse in time. And again, this was a concern based on physics, and many people who are optimistic simply dismissed it and said that, yes, you will be able to create remarkable novel thermodynamic behavior. And the most important concerns about quantum computers is about the errors, noise, and this was raised in the mid-90s. And the response, which is a fairly strong response, said that quantum error correction and quantum fault tolerance will solve the error problems. There were several notable counter-responses. For example, people claim that fault tolerance is based on unphysical assumptions, and this is a main part of the ongoing debate. And it's also claimed that implementing quantum fault tolerance is ridiculously hard. This is, for example, the point of view of Michel Diakonov, and the response is that it is very, very hard, but not ridiculously. Let me zoom in on three computational complexity-based skeptical claims and responses. And the first one that I already mentioned is that quantum computer violates the extended Turing thesis that represents our understanding of the computational world. And people said this is a feature and not a bug. And they also noted that factoring is very low in the complexity world. We should not make a fuss over it. It is not like that quantum computers can solve NP-complete problems. Another concern that was raised around 2005 is that people realized that quantum computers would allow us to sampling tasks that are beyond the entire polynomial hierarchy. So it's not just factoring. It's something which goes, it does not contain all the NP-complete problem, but on the other hand, it goes beyond the entire polynomial hierarchy. And this could be a serious reason to doubt that the model is realistic. And moreover, it turns out that you don't need the full power of quantum circuits. You only need bounded depth quantum circuits. So bounded depth quantum circuits already have this fantastic computational power. And again, the optimistic just regard it as a feature and not as a bug, and raise the idea around 2010, we'll come back to it, that quantum sampling power, we can use quantum sampling power to demonstrate experimentally the so-called quantum supremacy, the ability of quantum computers to sample probability distribution that it will take an ordinary supercomputer millions of years to sample. An additional computational complexity-based skeptical claim that I already mentioned was raised in my work with Guy Kindler from 2014 and my subsequent work. And this says that robust computation on NISQ systems represent, and I already mentioned it, primitive computational power. Consequently, NISQ systems cannot demonstrate quantum supremacy or good quality quantum error correction. So this is the basic new ingredient in my approach. And I think this is a fairly strong argument. It's not a definitive argument. And I think people who are enthusiastic about quantum computers say that, no, we can use even NISQ computers, noisy intermediate intermediate scale quantum computers to demonstrate quantum supremacy, and the matter is now at the hands of the engineers. Okay, so this was a brief assessment of my theory and some other skeptical claims. And now I want to make a brief assessment of the progress in the past decade. And here, let me start with David DiVincenzo. I should say that the entire presentation can be downloaded, uploaded, whatever, from my blog. And this contains some material and some links that I will not elaborate on. But this is quite an important slide. This is a famous 7-step roadmap to quantum computers. So David DiVincenzo proposed it in 2000, and there are 7 steps. The most advanced step is fault-tolerant quantum computation. And I think the crucial step is to find logical memory with longer or substantially longer lifetime than the physical qubits. So to demonstrate the idea of quantum error correction by starting with physical qubits, which are noisy, and then building some quantum error correcting codes and producing something which is much better, 10 times better, 100 times better. It can even be 10 to the 18 times better. And the way the situation now is that in 2025, we do not have good quality logical qubits yet. We have some claims of improvement by a factor of 2 or something like that, but not a substantial improvement of some ingredient or of the quality of quantum computers, but not substantial improvement of the quality of logical qubits. And this is one of the crucial ingredients. And there is a good theoretical argument. So this is an argument that I made based on my work with Kindler, that achieving good quality logical qubits is beyond reach for NISQ circuits. So this good quality good quality logical qubits, to achieve them, it's even harder than to achieve quantum supremacy that we will come in a minute. And also they represent probability distribution that cannot be demonstrated with this primitive computational power. Okay, so this was the worldview, or the main worldview. It's still the worldview today, but about 15 years ago, there was some new ingredient that people introduced, and they thought to insert between stage 3 and stage 4 of DiVincenzo to insert a new stage, which will consist of proof of the concept for quantum computers. And the idea was to use noisy intermediate scale quantum computers for demonstrating the so-called quantum supremacy, demonstrating tasks that the quantum computers can achieve much, much better than classical computers. And again, there is a good theoretical argument that I mentioned by me and Guy Kindler, that quantum supremacy requires quantum fault tolerance. You cannot shortcut quantum fault tolerance and achieve directly quantum supremacy. The probability distribution coming from noisy intermediate scale quantum computers are very, very primitive. On the other hand, there are some fantastic quantum supremacy claims, and those claims are unconvincing. So there are, I will mention some of these claims. There were claims for many years, but these claims are not convincing. There is yet let me mention that one thing you can do for the 7 steps road, if you want to assess the progress, is to look to a very good lecture by John Martinez from 2013. This was actually a conference that I was one of the organizers in Jerusalem. And Martinez described the state of affair at that time in terms of the quality of the individual components and his expectation to the next few years. And you can see that these expectations are not even fulfilled, are far from being fulfilled today at 2025. Let me move on to topological quantum computers. And here, the idea is to shortcut the first 4 stages for the circuit model and to build a new phase of matter called Majorana zero mode, and there are some other suggestions. Those phases of matter are called the non-abelian anyons. And if you succeed in building this physical gadget, which are extremely interesting from the physics point of view, then you can use them, and this is an additional complicated engineering science to build topological memory with longer lifetime than physical qubits. So you jump directly to the Vincenzo 4th stage, and you can even implement operations using some physics or braiding, or at least some of the operation. So you have a simpler way to achieve something which is analogous to quantum error correction. And the situation now is that there was some effort in this nice idea, and the claims of Majorana zero mode are unconvincing. So let me show you a question and answer from a site. It's called Quantum Computing. Does Google error correction paper invalidates Gil Kalai's argument? And so this was a question by a participant called Tristan Nemoz. I personally like scientific activity over the internet and these questions and answer sites, especially mass overflow. It's very useful. And this was answered by Craig Gidney, who is a member of the Google team. And he wrote, I think experiment of this type will refute Gil's argument, but I would be uncomfortable claiming that yet. I like nice, clear, don't even really need statistics answers to questions like this. So personally, I'll be waiting for a 1 in a trillion error rates on complex states before saying the physical noise is conspiring position has become indefensible. Now, 1 in a trillion error rate for a complex state is really some task, very fantastic numbers, but this is roughly in the ballpark of when you need to worry that Shor algorithm will be implemented for factoring large numbers. So this is a fantastic future goal, but this is what is needed for Shor algorithms. When I saw this answer, I immediately said that I would admit that my argument is refuted much before 1 in a trillion error rate on complex states, and even 1 in 1,000 error rate on complex states will convince me. The situation now is that if you consider complex states on, say, 30 qubits, then it depends how you measure it. The level of error is between 90% or between 90% and 100%, depending on the way you measure the error. And this task is very, very, so on the one hand, it's something which look very remote from today's reality and level of progress. And on the other hand, this really represents what is needed for show algorithm, so that we will start worrying that somebody will factor some large numbers that are used for cryptography. Okay, so let me move on to the next point of disagreement with Matthias. Matthias says that the research is well on track. And my view is, again, it's partial disagreement. My view is that I agree that a lot of brilliant people are involved in this endeavor. There are good ideas and innovation. There are, however, also concerns about correctness, transparency, and scientific conduct of some major experimental claims. In general, published experimental claims are often not properly scrutinized. So, my theory is consistent with the outcomes of credible experimental progress. Now, I should say that we had a debate which was very friendly, and also this is similar. I had another debate 12 years ago with Aram Haro, which was also friendly. And this was perhaps one of two isolated points, but there was a little tension because Matthias strongly disagreed with my claim that experiments are not scrutinized. You can watch the debate over YouTube, and he claimed that everybody can scrutinize some experimental claims. And this is a complicated matter which goes beyond the specific area of quantum computation. And in any case, our hosts were quite happy that at some point we don't have this idea, that we disagree, and we are really got a little angry or something like that. Okay, so moving to experimental claims, we study carefully a claim by Google that claim to achieve quantum supremacy using samples. So they claim that they produce samples in 5 minutes that would take a supercomputer 10,000 years. And we had a careful analysis of their work and also other people. So other people studied the complexity claim, and they found much better classical algorithms. So in particular, the classical algorithms are 10 to the 10 times better than the numbers that Google claimed, and therefore, for this particular sampling task, we can do it also on classical computers in about 3 minutes. But our study shows that there are additional concerns regarding the Google experiment. Some aspects of the experiments are statistically too good to be true, which raise concerns about the quality of the data. The calibration method indicate what can be called a stone soup, that there was some optimization, undocumented optimization toward the goal, and there is lack of transparency in crucial data for various reasons. And very recently, there are even the additional fantastic claims. Google in December claimed that the quantum computers achieved in a few minutes a computation that would require 10 septillion years for a classical computer. I didn't know what septillion is, but septillion is 10 to the 24. So they claim that in few minutes they can achieve computation that will take 10 to the 25 years for a classical supercomputer. So this is quite a claim. And my theory, I think it's fairly strong, but it is not strong enough to prevent people from making baseless claims. And Microsoft, 2 months later, claimed to achieve the first topological qubit. It was created. It is based on a new phase of matter, Majorana zero modes, and probably probably these claims are incorrect. But yeah. So maybe I will go to one slide, which is somehow, especially, so I didn't study carefully the issues of crypto money and post-quantum cryptography and vulnerability, but I would make the following advice. First, make a comprehensive study of available post-quantum cryptography and the relevance of post-quantum cryptography to gaining additional security in any specific case. So, second, wait in implementing post-quantum cryptography for a firm demonstration of DiVincenzo's steps 4 and 5, and we are still far from this stage. Of course, one can study this matter beforehand, but there's no reason to do anything before we have a firm demonstration of these milestones. Okay, something banal is to implement post-quantum cryptography as an additional layer. And in my judgment, it is implausible that you will see a Shor algorithm implemented in the next decades. And if my theory is correct, not even later. And something which I think is important, independently scrutinize far-reaching experimental claims. The incentive in the scientific academic community to double-check fantastic claims are not high. And if you study this matter seriously, you need to do some scrutinizing for claims, and also to scrutinize yourself. And whatever you do, be open and transparent. So here's my conclusion. There are compelling, though not yet definitive, arguments for the failure of quantum computers, as well as for inherent obstacles to near-term goals. Exploring this avenue represents intriguing scientific challenges and could have significant implications for various areas of quantum physics. So here is the end of my, at least first part. And now we will be very flexible on how to proceed. So thank you very much. Okay, I think I should mention this is not a duel. This is an exciting scientific debate. And there are some, let me just tell you what I have prepared. So there is a menu of things that we can choose from. I can tell you more about the background of quantum computers. What is computation? What are Boolean circuits? What are quantum circuits? And what does it mean? Efficient computation, noisy computation. I can elaborate on my argument against quantum computers. This is the third part of this presentation. The fourth part is even going deeper into the mathematics and describe the mathematics behind noise stability and noise sensitivity, basically based on the case of boson sampling, which is particularly exciting. The fifth part is about the failure of quantum computation. What are the underlying principles and consequences for physics? And the sixth part is our statistical analysis of Google's 2019 experiment. So this was a major project on its own right, and it's raised quite interesting issues about statistics. So this is the third part. And in any case, I'm quite happy to hear your questions and request and to move in any direction that you would like to. Okay.
Yes, so maybe it's good to take some questions here and then decide if we proceed to either of your suggested additions.
There are questions on the chat, by the way, Matan, just in case.
Right. So first questions, as I see it, is but I think you more or less answered, Gil, but maybe you could elaborate a bit. When do you expect we will know with high assurance whether or not quantum computers are possible?
I think, as since this is some sort of an ideal that people hope for, it will. I think I think we will know much better in the next decade if there will be major successes in the milestones that people pose. Then this will give us good reason for optimism, and then we can maybe convincingly say that the remaining tasks are engineering tasks, which are still be extremely difficult and will require many years. If, as I expect, we will see a clear barrier for the quality of qubits, whether they are topological qubits or physical qubits or logical qubits, we will see similar barriers. And then I think I think this would be a good indication that this argument is correct. And I think what we will need to study further is what are the implications for various other problems. So I think there is a good chance with the level of enthusiasm and investment that we will have much clearer pictures in 5 to 10 years.
You're muted, Matan.
Sorry. The next question is from someone who had to leave and says, I would love to hear your opinion on very recent progress on squeezing cuts and error correction. And he refers in the chat to some archive paper. And more generally, from a risk management point of view, how do you think existing crypto systems should prepare, or should they not? Quantum computing being akin to meteorite risk, low probably high impact. It's known to be a hard to manage category of risk.
Yes, I think I'm not an expert regarding how to manage risk. In general, I think the first rule, like in medicine, is do not do harm. So whatever you do, do not make your systems more risky, even if it will benefit a hypothetical situation of quantum computers. The second principle is don't do things that are useless. So it is possible that some solution will solve some issues but not solve other issues, and you will still be vulnerable. So then it's not a good idea to invest in them. But as I said, I think you need to weigh. I think one needs not only in any post-quantum, this is some advice I gave years ago. One needs to wait for a firm achievement of qubits, which are logical qubits, which are much better than today's physical qubits, either topological or by quantum error correcting codes. And this is not in sight, and in my opinion, you will not see it at all, but this is a good milestone to put before involving in complicated changes. But again, this involves a lot of other aspects, or I will let you judge. Is it possible to build quantum computers outside the NIST paradigm? So this is a very good question. so I mentioned topological quantum computing. Largely, my argument still hold for topological quantum computing, but it need to be expanded. The point is that we can, whatever we build, like we build non-abelian topological qubits based on non-abelian anyons, this is still can be simulated with the models of quantum circuits. So the argument that building that will not be able to build this gadgets transfer from the NISQ paradigm to the topological paradigm. But of course, there may be some other ideas for supercomputing, whether quantum or even non-quantum. What would a compelling experiment look like to you? One that might start to challenge your current beliefs. Again, okay, so I should say that the Google experiment or claims, had they been correct, would certainly challenge my current beliefs. As I said, that if their claims were correct, this would refute entirely my argument. But it turns out that the argument was incorrect, and the experiment is not cannot be trusted. So this is when it comes to a quantum supremacy experiment. And when it comes to quantum error correction, if there will be convincing demonstration of much better qubits using quantum error correction, then this will be this will be quite convincing. And as you see, I can also follow Craig Gidney's advice and wait for complicated quantum states that you can achieve with error of 1/trillion or even 1/1000. A lot of this research has high business value, national security implication. In the case of fantastic claim that is not made public, what would be necessary to convince? I didn't understand this question by Uilome. What would be necessary to convince me for fantastic claims that are not made public?
I mean, I just meant like my understanding, at least, of your reason to brush aside the claims by Google and Microsoft from this year and last year, where that none of that was really explained. So it was it was just as we call in our space, trust me, bro approach. And yes, I'm just saying, like, people could claim that they have reached quantum supremacy, but not provide any proof of this, because there's good business reasons or maybe just national security reasons. What would be a way
No,
to?
I don't think the issue with Google is national security reasons. It's true that we suspect that the calibration method is not contain an undocumented optimization process, and this is they kept a secret, but not for national security reason, but for a commercial secrecy. But there are some mundane data that they still didn't made public, like the error rate for the two gates in the 2019 experiment, and there's no reason why this cannot be public, and this is sort of a problem that is not only unique to Google. There are some difficulties in gaining data from experimenters in some cases. Now, yeah, so and I don't think people, I don't think there is some fantastic achievements that are kept hidden in some other places. Can you scratch? Okay, this is a good the argument that limits NISC to LDP. So this is part of the presentation that I can go over. Can error-prone quantum computers still reduce the amount of work necessary to break cryptography? I don't think so. So I think there is here a dichotomy between two beliefs. One analysis, which is very optimistic, very appealing, is that the power of quantum mechanics will enable us to make computations that are much superior to classical computers. And the other point of view, which is supported by my analysis, is that quantum computers quantum computers are computationally very primitive, and there is one mechanism to make them to get some robust information out of them, and this mechanism is roughly repetition and majority, and this mechanism gives you robust classical information. It's not clear why do we have at all classical physics and classical information. This is the only mechanism to get something useful from information point of view from this very primitive low-level computational power. And therefore, I don't think that quantum computers, I don't know what error-prone means, they cannot be error-prone. The only way to make them error-prone is to make them classic, and they will not be useful to break cryptographic or for any other algorithmic purposes. Okay. I've heard it said before that the speed with which we can expect to see quantum computers is heavily dependent on the amount of engineering investment in the area. Once the research breakthroughs are sufficient, the engineering effort was linked to the Manhattan Project. Is this sentiment you agree with? Yeah, no, I think right now the bottleneck is very small systems, is the ability to have good control on systems with 10 qubits, with 15 qubits, with 20 qubits, and the investments are fairly reasonable. I don't know, it is within millions of dollars a year. So, you can always think that if you replace this $1 million by $1 trillion, then you will be able to do something better. But I don't see evidence for that. Of course, it's possible, but I think there's no evidence that this is the case. What is the best utility when this even fault materialize? I don't think NISC computers is sort of a fun physics experiment. I don't think they will be useful for anything if you don't, they're not useful for computational purposes. Are there any limitations on the quantum limitation roadmap related to the no cloning? Yeah, I think, for instance, if we would copy, copy qubit data. Okay, so I didn't understand the question of C. Perez completely, but it rings something that I thought about, and it's actually quite. And this is the following. So I think this is a nice example. The no cloning theorem, it's a firm mathematical statement that says that if you have an unknown quantum state, you cannot clone it and get precisely the same state. Now, the point of view of noise sensitivity tells you something stronger, that if you have a state obtained by a 12-qubit computer even if you know even if it's not an unknown state, even if it is a specific state, then you cannot clone it, or you cannot achieve the noiseless state within good accuracy. And this is in contrast to what Craig Gidney expect us to do. You cannot, for complicated states, even on 12 qubits and the depth 14, there will be inherent noise sensitivity, which means that you cannot clone such states at all, whether they are known or not known. So for unknown states, this is a firm mathematical statement. For known states, this is something which go beyond the mathematics, and this relates to my argument. So this is part of a variety of cases where if we assume that we live in a world devoid of quantum fault tolerance, then some insight from physics becomes stronger, and no cloning is an example, time energy uncertainty is another example, and there are yet other examples. Okay, so good. So maybe I will. How would you think people working on this? Why do you think people working on this disagree with you? Hope something else. No, I think I think it's entirely okay to disagree with me. I don't, I raise my argument, and people, as you see, there is something. The crux of the matter is if this computational complexity reasoning can apply to engineering, to convince that there is a limit to the engineering efforts. Now, I think people perhaps believe that this is not the case, and I think I'm quite glad that people invest so much money in these engineering efforts in many directions, and ultimately this matter will be decided experimentally. I don't see much advantage if the billion level or tens of billions levels of investment will be increased to 100 billions, because the deadlock is still very close to to the starting point in terms of systems with many qubits, with 10 qubits, with 20 qubits. So why do people disagree with me? I think I try my best to talk with them, to convince them, to be convinced by them. Yeah, so out of the current project to create computational supporting qubits, the photonic trapped ion topology, which do you think has the best chance to scale to supporting low noise qubit states? We looked at several experiments in various directions. My particular argument is blind to the precise method, whether photonic or trapped ion, so I don't see any method which has an advantage as far as my argument is concerned. And I think it's good that people try many methods. Okay, so one thing I can do is I can go back to my slides and go back to places where people raise questions, and let me see if I can do something which will be of interest. Let's see. Now, okay, so let me share. So if you So I cannot move the screen, so let me stop share and do it again. Okay. Some reason let me try once more. Now it looked like, okay. So if some of you want to, okay, there is one question that was not raised, but okay, it doesn't work. Let me try once more, and if not, I will do it without the slides. For some reason, oh, okay. I don't know why it didn't work. Let me go to 1 minute. Okay. Let me try now. Okay, so let me see. Okay, so there was a question that you didn't ask, so I will not answer, but I will just give you as a food for thought. People often ask me if I claim that quantum supremacy cannot be achieved, and they say, maybe the problem is that we cannot harness quantum supremacy, but it looks obvious that if without noise, the state represent computational complexity supremacy, then the noise make it even harder to simulate it on classical computers. So isn't it the case that we have quantum supremacy in nature all around us, and it's just a matter of harnessing it? So this is not the case, and I will leave it for you to think why this argument is incorrect. Okay, so there is in those slides some slides about the very basic of what are quantum circuits, what is noise, what is computational complexity. Now there are two parts about my arguments, and I think maybe the best thing would be to tell you briefly about boson sampling, which is very nice mathematics, and about the theory of noise stability and sensitivity, which is behind it. So I don't know if I can try to, it works. So here are some people dealing with this theory. So noise sensitivity and noise stability is a mathematical theory that was developed by Itai Binyamini, Oded Shram, and me in the late 90s. And a similar theory under a different name was developed by Vershik and Cyrelson. And many people studied it. For example, there is a book about it by Garban and Steif. And next week, there is even a birthday conference for Jeff Steif. And the work that related it to quantum computers and specifically to boson sampling was done by Guy Kindler and me. So let me tell you a little bit about this work. This gives the reason why NISQ systems in general and boson sampling in particular represent a very low-level computational class. And what is this low-level computation class? And the mathematics is very nice, and it starts from a complex n by m matrix with orthonormal rows. And the task, the computational task, which is a little bit peculiar computation task, is to sample the m tuples of columns with repetition according to the absolute value squared of the permanent. And this task is referred to as boson sampling because non-interacting bosons perform this task. And the quantum computers can perform boson sampling on the node. So if you have fault tolerance quantum computers, certainly if you have noiseless quantum computers, but even fault tolerance quantum computers, you can achieve this distribution precisely. And this task is beyond reach for classical computers. And this is based on some standard computational complexity conjectures. And in fact, not only it's beyond reach for classical computers, it's beyond reach even if the classical computer is equipped with an oracle that have the entire power of the polynomial hierarchy. So this is a very complicated, very difficult task for non-classical computers. So here is an example. You can see this matrix 3 by 2. This is not very difficult to do. And we can consider every pairs of columns, compute the permanent. If we have repetition, there is some normalization factor that I will not mention. And we have this distribution for the pairs of columns. And if we use determinants instead of permanents, this corresponds to fermion sampling. So another major physical object. And fermion sampling is something that classical computers can do quite easily. And what we did was we said, okay, let's try to make a model for noisy boson sampling. We take a complex Gaussian matrix, and we start with an input matrix, which usually we think about it as a Gaussian matrix, and we add to it some noise matrix. And this is the formula, and we have a certain rate of noise. So this was an artificial mathematical modeling of the noise. It turns out later that this model is also quite relevant to the physics. It represents one notable source of noise in the physical realization of boson sampling. And then what we did is we expand the outcomes in terms of the Hermite polynomial. And the effect of the noise, and this is the crux of the matter, is that the high terms coefficients decay exponentially. And this led to two theorems that we proved in 2014. The first theorem says when the noise level is constant, this relates to the question, what is LDP? When the noise level is constant, distribution given by the noisy boson sampling are well approximated by their low degree Fourier Hermite expansion. consequently, this distribution can be approximated by bounded depth polynomial size circuits. But bounded depths, they can be approximated by polynomial of bounded degree. And this is even stronger than the statement that they can be approximated by bounded depth polynomial size circuits. In any case, this is the computational complexity class that aroused in this work. It is probability distribution that can be well approximated by polynomials of bounded degree. So this was our first theorem, but we had another theorem, and it says that if the noise level is larger than 1 over n, so much lower level of noise, noisy boson sampling is very sensitive to noise, with a vanishing correlation between the noise distribution and the ideal distribution. So this means that I think the interpretation of these two results is that when you do realistically noisy boson sampling, and it extends to noisy NISQ circuits, you have a robust component, which is described by low degree polynomial, and you have a noise sensitive component, which is where your samples have zero correlation with the ideal distribution. And not only they have zero correlation with the ideal distribution, if you change a little bit the parameters of the noise, the result will be uncorrelated to the original form of noise. And this is the meaning of noise sensitivity. This is the reason why you cannot get anything. So with some level of noise, you get only low degree polynomial, but then there is a whole range of noise beyond this level that you get something which is completely unpredictable, unstationary. And as a matter of fact, the samples, there is no the underlying distribution. The samples are function of the noise at the samples, even the bits, the individual bits, are function of the individual noise at the time that they were created. So this was the two theorems that we proved. And now, I think, okay. And this is the picture. No, this. No. Okay, this is the picture. So we have this discrepancy between boson sampling and fermion sampling in the ideal world with no noise. One of them is in the polynomial hierarchy, actually not in the hierarchy. One of them is polynomial in terms of complexity. The other one go beyond the polynomial hierarchy. But when we add noise, or these two ellipses, the green and the purple, they all shrink to the very little region of bounded depth computation. And inside this bounded depth computation, they belong to even much smaller region, which is this LDP, probability distribution that are described by polynomials of bounded depths. And then there is no distinction between fermions and the bosons. And I should say that in nature, in physics, there is no distinction between fermion and boson that resemble this huge computational task, a gap in computing them. So this was the result. This is the basic mathematical result that we proved. And we conjecture, I conjectured, and there was some work that both these theorems extend to all NISQ systems, and in particular to noisy quantum circuits and to all realistic forms of noise. And I should say for boson sampling, other forms of noise were studied by various people, and they satisfy this conjecture. Okay, so this gives more or less some picture about what is this complexity class LDP and what is the argument. I think the argument is okay. Let me stop share. The argument is outlined in more details in some other part of the talk, and as I said, there is some crux of the matter. The crux of disagreement, let me just mention it to you, that I argue that the point of view of computational complexity, NISC devices are in fact low-level classical computing devices, and I regard it as strong evidence that engineers will not be able to reach the level of noise required for quantum supremacy and good quality quantum error correction codes. So this is my point of view, and here I don't think this is a fairly early milestone in what people try to do. I think the hundreds of millions dollars invested give a good chance for achieving it. I don't see maybe some, I don't see that money is now the problem, but maybe it is. But in any case, this is the theory. And others, and this refers to the question why other people are not convinced, others argue that the existence of low-level simulation in the NISC regime for every fixed level of noise does not have any bearing on the engineering question of reducing the level of noise. So these are two sharply different views. They cannot be decided by some mathematical theorem, and they will be tested in the next few years. So I think this may be a good place to finish, unless you have some more questions, or maybe you do already have some more questions in the chat. No, so let me end here, and I welcome few more questions, and it was nice to talk to you.
Okay, thank you, Gil. It was very enlightening, and I hope many participants got new point of view from it. Unless there are other questions, I would like to thank everybody that came, of course, Gil, and also Barnabe that helped creating this invited talk. Yes, and we'll see each other probably in Berlin.
Okay. Thank you. Bye-bye.
Thank you.